So here in 11.2, we're going to show you the world's simplest router. So what's the world's simplest router? Everything lives on a simple grid. All of the wires have exactly 2 pins, so they have a starting point and an ending point, which are traditionally called the source and the target. All of the routing takes place on one physical layer of material, so think of that as one layer of metal available on an ASIC. You can't change any layers, and your only goal is to connect the first pin to the second pin. The mechanics of that are surprisingly straightforward. It's a maze search process, and depending on what sort of computer science you've done in the past, you might have actually written code to do something like find a path through a maze. It's a famous classical problem, and interestingly enough, it's the basis for essentially all routing that we know in the ASIC universe. So let's go look at the simple routing problem for 2-point nets.
So let's start our discussion of the most basic kind of maze router with just a little bit of history, I guess history, if you will, after Moore's mazes. So 1959, Moore publishes this basic idea, a certain kind of a breadth-first search through a grid, and it's really famous. In 1961, just a couple of years later, it gets applied to electronics, and in this case, the wiring of printed circuit boards. And so a person named Chester Lee at AT&T Bell Labs publishes a famous paper, An Algorithm for Path Connections and Its Applications. And he basically says, you know, this idea from Moore for how you find a path through a maze, that's kind of like routing things on printed circuit boards with obstacles. And he gets famous for sort of making this connection. And for something like a quarter of a century, all of the routers that are these kinds of routers are called Lee routers. When I was in graduate school, these things were called Lee routers. In 1974, almost 15 years later, Frank Rubin, who was working at IBM, makes another interesting connection. He's reading some of the early developments in artificial intelligence, people doing certain kinds of search algorithms, and he says, oh, some of these interesting ideas in AI can be applied to this particular search process, and you can make it go much faster. And so, interestingly, he says, you know, the title of his paper is the Lee Path Connection Algorithm, which is, again, you know, Lee, that guy, Chester. And that's another core technique that gets used in everybody's router today. And then in 1983, Dave Hightower, who's a very interesting guy, publishes another paper called The Lee Router Revisited. And it turns out for something like a dozen or so years, previously people had said in the industry, you know, this Lee router thing, it's really great, but we just don't have enough memory in our computers to build the grids that represent the things we want to route, and so we're going to do some other interesting, clever kind of algorithms. And Dave Hightower got famous for another kind of a router, a thing called a Hightower router. And so it's a remarkable conversion when Dave publishes a paper that says, you know, modern computers, you know, computers with something astonishing like 8 megabytes of memory and a virtual memory hierarchy, so you have a disk that can store things that are bigger than 8 megabytes. You know, if you have a modern computer, you can actually use a Lee router. You can actually use a grid. You can actually use this really great algorithm. It can route really big, really complicated stuff. And, you know, it's sort of from that point thereafter that there's no looking back. You know, most modern routers use this kind of idea. So a little really early history if you care. So the maze routing strategy at a high level is that we're going to route one net at a time. We're going to completely route the one net, and then we're going to move on to the next net. And we're going to optimize the path of the net. We're going to find the best wiring path for each one. And so there's some problems. Early nets that are wired may block the path of later nets. That's actually easy to see in a little example. You know, the optimal choice for any one net may not be good for a later net. So, you know, I route this pair of 2 points with this wire on one layer. I route this pair of 2 points with a wire on one layer, and then I'd like to route those 2 pair of red points there. And, you know, what do I see? I see that I can't do it. So, you know, I've got these 2 little sort of elbows going up and to the right. That are blocking basically the horizontal left to right accessibility in this little rectangle. And then I've got another little elbow that goes from below to above, and those 2 blue wires are simply obstructing it, and I can't get around them. On one layer, I can't get around them. If I have multiple layers to route, I can get around them by going up to a different physical wiring layer. So that's a non-trivial problem. We're going to have to figure out that. We'll talk about that later. So blocked. That's the word. It's blocked. So the basic maze router, the basic idea is that you're going to give me a grid, and each square cell represents where one wire can cross. And we're going to start by connecting 2 points, and the points are historically and traditionally called the source and the target. You start from the source and you route to the target. And the problem is to find a shortest path connecting the source cell and the target cell. And so when using the cells, a wire can, for example, it can cross the cell, so you can cross vertically, you can also cross horizontally, or you can bend. You can go into the cell and you can sort of turn and go out sideways. So you can do anything you want in a cell. As you can just assume that all the geometry is correctly set up so that any wire can cross any cell. So that's how it works. So what's the big core idea of a maze router? You start with the source cell, just this single cell. And then you find all the new cells that are reachable at path length 1. And so what that means is, what are the ends of all of the paths that start at the source that have exactly 1 unit of total length, which is to say that are 1 cell long? Mark them all. Well, interestingly enough, it's just the 1 cell, right? What are all the cells that are 1 cell long that start at the source? And the answer is the source. That's it. Well, but then there's a more interesting question. What are all the paths that are 2 cells long that start at the source? And the answer is, those are all of the cells that are adjacent in the north, south, east, or west direction, right? So there's the cell that's adjacent on the north, there's the cell that's adjacent on the south, there's the cell that's adjacent on the east, there's the cell that's adjacent on the west. And basically it's all the cells in the grid that are immediately adjacent to the cell labeled 1. And so what you immediately see is this little diamond pattern, right? There's a 1 in the middle, and there are a little sort of a diamond, a 2 above, a 2 below, a 2 to the left, and a 2 to the right. Or, if you like, a 2 to the north, a 2 to the south, a 2 to the west, a 2 to the east. The big idea in maze routing is you just continue this process. That's the big, great idea. You find all of the paths that are 3 units in length. Well, those are the paths that are 1 unit of cells farther away from the 2s. You find all the paths that are 4 units in length. Those are all the cells that are 1 unit away from the 3s. And you just keep going until one of those cells labels the target with a path cost, a path length, and you found a path. So we're going to do this one by me writing, and then we'll do these with animation thereafter, but it's worth just sort of, kind of doing it yourself if you like. So what do? We start with the source cell. We say, what are all the paths of length 1? And the answer is, it's that one. Okay, what are all the paths that have length 2? And the answer is, it is this diamond of cells north, south, east, and west of the source 1 cell. Okay, what are all the paths of length 3? And the answer is, it's this diamond of cells, right? And when I say diamond, I mean basically things that look like that. It's this diamond of cells that are 1 unit away from the 2s. Okay, what are the paths that are of length 4? And the answer is, it is all of the cells that are 1 unit away in the north, south, east, or west direction from the 3s. Okay, so there's a little more of the diamond, and one of the things you see is that I'm not getting the entire diamond because some of it, I can't do 4s on the north and the left side, the north and the west side of this chip because the source is up in the left corner. All right, where are the paths that are 5 units in distance? And the answer is they are 1 unit away from the 4s, so the diamond keeps getting bigger. Where are the paths that are 6 units in length? Oh, well, those are the ones that are 1 unit away from the 5s. Where are the paths that are 7 units away? Oh, look, they are also 1 unit away from the 6s. Oh, look, I have hit the target. I have labeled the target with a number, and the number I have labeled the target with is a 7. What does that mean? There's a path of length 7 from the source to the target. Sounds simple. That's the deal, right? There's a little bit of language we're going to revisit here. Each of these expansion steps, going from the 3s to the 4s, going from the 4s to the 5s, going from the 5s to the 6s, creates a wave front of paths. And the analogy is usually, if you drop a rock in a pond, the waves, sort of go out in a circle. Well, in this case, the waves go out, if I kind of draw it here, the waves go out in a diamond kind of a shape. So that's the core idea. Now what do? Well, you do a step called backtracing, but before we do that, let's just do that previous step again, but we're just going to do it with animation so you can see it with nicer looking handwriting, right? So where are the cells on the paths of length 1? It's just the source cell. What are the paths of length 2? It's the diamond around the 1. What are the paths of length 3? It's the diamond around the 2s. What are the paths of length 4? 1 unit of cells away from the 3s. What are the paths of length 5? 1 unit away from the 4s. Where are the paths of length 6? 1 unit away from the 5s. Where are the paths of length 7? 1 unit away from the 6s. And what we have discovered here is that I have labeled the target. I've labeled it with a 7. Okay, now what do? I do a next step called backtrace. Select a shortest path. Any shortest path. There's actually several shortest paths. There's lots of paths between the source and the target. Select one. Mark the cells so they cannot be used again. In particular, we're going to mark them as obstacles because this path, once we embed it as a real wire, is an obstacle. The next wires I route cannot use this space. And since there are many paths back, this optimization information can be used to select the best one. This particular case, it's really easy. How do you do this? And the answer is just follow the path lengths in the grid. So you want to find a path from the target to the source. The target is a 7. Find a 6. From the 6, find a 5. From the 5, find a 4. From the 4, find a 3. All right, so we can simply do that. And what will happen is I'm going to choose the horizontal path 7 to 6 to 5 to 4 on the sort of the second row of the grid on the bottom. And then continuing, I'm going to choose the vertical path 4 to 3 to 2 to 1. And so those pink cells are the backtrace result. Once the target is labeled with a number, go look at the grid and follow the numbers backwards in decreasing order until you find the source cell. That's your path. Then what do? You do a step called cleanup. And cleanup is just what it sounds. Cleanup says get rid of all the stuff you put in the grid so that the grid is in a state ready to route the next wire. So if you just put some path length numbers in the grid, please go erase them all. And let's also just make sure that you relabeled the path you just found as an obstacle because the next wire cannot use any of those cells. So it's got a big black L-shaped thing right in the, kind of in the middle of this grid saying, oh, look, I have embedded a path. And now this grid is ready to route the next net with previous nets represented as obstacles. Now, the obstacles we sometimes call them obstacles, we sometimes call them blockages. Any cell you cannot use for a wire is an obstacle. An obstacle or a blockage. There may be parts of the routing surface you just cannot use, so before the problem even starts, we'll have labeled those things. But the biggest thing is you label each newly routed net as an obstacle, and so future nets will route around. So as a little example, I'm showing a new source and a new target here. And if I was going to route this net, I would be doing, exactly the same sort of a thing. I would say, oh, look, you put a 1 down, you find the paths of length 2, they are 1 unit away. You find the paths of length 3. They are 3 units away. And now you see I've got an obstacle. I can't expand those 3s anymore. You find the paths of length 4. Those are the ones that are adjacent to the 3s. You find the paths of length 5, and you see this interesting phenomenon here. Oh, look, I'm sort of going around the obstacle. You find the paths of length 6. Oh, look, I'm going around the obstacle. You find the paths of length 7. Oh, look, I'm going around the obstacle. You find the paths of length 8. Oh, look, I'm going around the obstacle. You find the paths of length 9. Oh, look, I found the target. Right? If I backtrace things back, what I'm going to find is a wire that probably looks something like that. And hey, I embedded the first wire, I made it an obstacle, and the maze routing idea of expanding outward paths of length 1, 2, 3, 4, by just looking at the neighbor cells, I'll actually respect the obstacle. I'll actually respect the desire to find a shortest path. I can do very many interesting, realistic physical things with a pretty simple algorithm. It's a beautiful thing. It's very famous. Lovely, lovely result. So that's the basic idea. Summarizing the 3 big steps, expand. A breadth-first search to find all the paths from the source to target in path length order. Why do we call it a breadth-first search? You find all the paths of length 3 before you find the paths of length 4. You find all the paths of length 4 before you find all the paths of length 5, and so on. Backtrace, walk a shortest path back from the source, back to the source, and then mark the path cells as obstacles so that you can keep routing, and then cleanup erases all the other stuff you put in the grid, returning it to its original and pristine state so that you can route the next net with the previous nets represented as obstacles. So that's the basic idea. It's pretty powerful, but to be honest, a little limited because there's just a lot of physical stuff in a real routing problem we haven't dealt with. How do I route something that has more than 2-point nets? How do I handle more than one routing layer? How do I deal with vias that physically connect from one layer to the other? And I haven't really told you anything yet about implementation. You know, do I really need a big grid? What information do I have to put in every cell in the routing problem? Do I really have to search the whole grid every time I do one of this? You know, I mean, there's some tricks that make it go fast, and the answers are, yeah, there's all kinds of tricks. There are things that make it go fast. So we're going to look at both kinds of concerns. We're going to look at the applications and features components for the first couple of lectures in the next set to understand how you handle things that are really required in a router. And then we'll move on to the interesting deep implementation stuff, the sort of the more computer science-y kind of stuff, like what do the data structures look like and what do the algorithms look like. So let's get started on that. We're going to start adding some features to our core router next.